Hi, welcome back. Last time we derived the fields, I'm just showing the electric field from a moving point charge as q over 4 pi epsilon 0 n caret. That's the normal vector from the charge to the observation point over gr squared. G is a Doppler factor. This is all evaluated at the retarded times, and then the same constant and the derivative of this thing. And what we need to show is we need to show that this is equal to that. And to do that, first I want to derive some identities. We have the definition of the retarded time. T is equal to TR plus R TR over C. In other words, a point at a time, earlier time TR, at this distance away, traveling at the velocity of light, and then adding it to the earlier time, we get to the current time. So a signal just this time to travel from the retarded time and the charge at the retarded time to the observation point. And so just taking a derivative here, we get dt dtr is equal to 1 plus the 1 plus dr, sorry, tr with respect to tr vector, and this is equal to 1 plus 1 over c times minus nr caret dot c beta r, which is equal to 1 minus beta dot n, that's unit vector, n hat, retarded. We call this equal to g, or I'll put the r on it, gr. So again, just to go back to the visual thing, this is the path of the charge. Let's say this is where it is now. This is the observation point. But we look at it when it's like over here, so that it can emit a signal to us like that. So this is R, and this is R0 at TR, and this is R0 at T, and this direction has a unit vector n caret at TR. So if we want to know, and R is equal to, in general, R minus R0. So, I'm sorry. So this whole thing over here is really just R. R0 is on, this is R0 TR, and this is like R at TR. So if we want to take the derivative of R, we would just take, this has no dependence, and it's just minus the derivative of R0 with respect to TR. And so we just have minus the unit vector times the velocity. And this would be beta at TR. So we're going to get a couple of identities which we're going to use quite often. 1 over gr is equal to the inverse of this. dtr dt, because this is, we just invert that and we get 1 over gr, and this is equal to 1 minus 1 over c ddt of r of tr, and This all comes from, I'm going to write down some more formulas here. You can all easily verify these things. Beta of R by definition is equal to minus 1 over C ddr of TR dTR, which is equal to minus 1 over C times dr TR. I'm using the chain rule here with respect to T times dTR, I'm sorry, dt dTR. So this is equal to minus 1 over C GR dr of TR with respect to T. Okay, so this last one, we'll use that a couple of times. I'll also derive another one that we'll use quite often, ddt n hat. And this applies at all times, whether it's retarded or not. It's just ddt r over r. And then now we use the usual calculus for taking the derivative of a quotient, minus C beta R minus R times dr dt, and we wrote over there, I derived what dr dt is, so this is equal to minus n hat dot C beta, and so this ends up being equal to n hat, I'm reversing the order of the terms, n hat dot C beta divided by R minus C beta over R. So we'll be using this, and this applies, we can at the current time, or we could put in a retarded time. Either way it would apply. And for those of you who want to do the magnetic field case, you'll need this. We won't do it, but this is easily derived from what we've done. This is equal to C over R n hat dot beta minus beta. But we won't actually need this one. We'll just need this for the electric. This would come in play for the magnetic. So using this, you'll end up, what you'll need for the magnetic is something like this, NR cross dNR dt is equal to, and this just applies from using a lot of vector identities. This is just the standard vector identity for the triple cross product, and then substituting in some of these derivatives with GRs and everything, you'll end up with this C over GR beta cross N retarded. So this will be useful for the magnetic field one. So I'm going to come back in the next video. I'm going to make liberal use of some of these identities, and we'll finally derive this formula from that top formula over there. I'll see you next time.